In this video, we're going to look at a brief introduction to the trapezium rule. We can use the trapezium rule to find an estimate for the area under a curve by summing the areas of trapeziums that are drawn under that curve. We would use the trapezium rule if we didn't have the ability to integrate the function we were given. So for example, if I needed to find the area trapped under the curve from 0 to 3 of 2x to the fourth plus 1, we can simply now integrate this. This is a polynomial. We can integrate and evaluate. That's a definite integral, and that would give us an exact area. Let's say we were given a function and we needed to integrate this from 0 to pi by 12, and we had 2 to the x multiplied by cos of 3x. We're yet to meet a function like this, so we don't yet have the ability to integrate this. So if I wanted to find an estimate for the area trapped under the curve from 0 to pi by 12, I could use the trapezium rule. The more trapeziums I draw, the more accurate our estimate for the area will be. Let's look at the formula that we're given for the trapezium rule. It says the trapezium rule is given to be the integral from a to b of y dx is approximately equal to 1/2 h multiplied by the quantity y sub 0 plus y sub n plus 2 lots of y sub 1 plus y sub 2 plus dot dot and so on and so forth, right the way up to y sub n minus 1, where h is equal to b minus a over n. When we look at that, it's quite bewildering. What I want you to do is grab a pen and write down an easier way to do this. What we can say is that the area will be approximately equal to h over 2. We're going to have the first value plus the last value plus 2 lots of all the other values added together. So other values added. And that is it. So all values, other values added. This is very formulaic, and later on in the video I'll show how it's done, but this is a lot better now in terms of understanding what goes where. Let's just look at this idea of h. h is simply the height of the trapeziums that we're going to draw. What I've got is a picture of a curve y is equal to x squared. So this is a curve y is equal to x squared. Let's say we wanted to find the area trapped under the curve from x is equal to 1 to x is equal to 4. We could say that the area was equal to the integral from 1 to 4 of x squared dx. We know how to integrate this and evaluate, so we can say that the area now is going to be 1/3 x cubed, and we're interested in this from 1 to 4. So substituting in, we're going to have now 4 to the power of 3, well that's 64, so that's 64 over 3, and we would subtract from that now. If I put in 1, that's going to be 1 over 3. So we can say the exact area using the definite integral is going to be 63 over 3, which is going to be equal to 21 units. So we can integrate that. All I've done is simply now integrated the polynomial and evaluated using that definite integral. What I'm now going to do is use the trapezium rule to find an approximation or an estimate for the area trapped under the curve from 1 to 4. So this time I'm going to use the trapezium rule. I'm going to say that I'm going to do it with 3 strips. So 3 strips. 3 strips gives rise to 4 ordinates. So if we have n strips, we have n plus 1 ordinates. The ordinates are simply the values of x that I'm going to put in here. I've chosen 3 strips. If I'd chosen 2 strips, the area, the estimate for it, would be further away from the actual value, so it'd be less accurate. If I chose 5 strips, it would become more accurate. So let's think about this. What I need to do is split this into 3 equal trapeziums. So if we look, I could go from 1 to 2, 2 to 3, and 3 to 4. The idea of h being b minus a over n is where we're getting this value of h. If I draw these up, it should make absolute sense of what's happening. So we're going to go now, my first trapezium is going to be from 1 to 2. So if I draw this on, we've got now 1 to 2. So that's going to go here and that's going to go there. This isn't massively accurate, but we can see already that this is going to be an overestimate for the area trapped under the curve, as the curve is slightly below the line of this trapezium. The reason being is that the curve is now concave, so it's opening upwards. If we were opening downwards, it would be convex, and we would have now an underestimate. We'll look at that later in the video. My second trapezium is going to go from 2 to 3, and we will come up here, and then I'm going to draw this down. So again, not massively accurate, but again, it gives us some idea. The final one, so creating my third strip, is going to go right the way up to 4, which will be just up there, and then we'll come down. So if we look now at the ordinates for x values we're going to introduce to this, we've got 1, 2, 3 and 4. So we've got 4 ordinates, that's x is 1, x is 2, x is 3 and x is 4, which gives rise to 3 strips. So let's have a look at this. All I'm going to do is build up a little table, and we're going to substitute the values in. So this is a very mechanical way of doing it, but hopefully it should make sense. If we think about this now, when x is equal to 1, if I substitute in 1, we're going to get this value, and that's 1 squared. Remember, this is the graph of y is equal to x squared. So the y coordinate is going to be 1. If I substitute in x is 2, substituting in x is 2, the y coordinate here is going to be 4. So that's going to be 2, and that's going to be 4. If I substitute in x is 3, we're going to have y is going to be equal to 9. If I substitute in x is 4, 4 squared is 16, and we can see that. Okay, so all we need to do then, if I want to use the trapezium rule, we can say that the area is approximately equal to h. H is just this height here. So when we talk about b minus a over n, think about the integral. This is a, this is b. So what I've done here, I've taken the integral from 1 to 4. So b is 4, minus 1, which is a. Now n is the number of strips, or the number of the trapeziums that we've used, and that's going to be 3. And that's why each interval is of 1 unit. So if I'd done now 6 strips, we would have had here now each height is going to give me a half. So what we can say is that the area is approximately equal to h over 2, the first value, that's the first y coordinate, plus the last value, plus 2 lots of the other values added. So others added. And I'm just simply going to sub this in. So added, there we go. So the area approximately now for the space trapped under the curve of y is equal to x squared from 1 to 4 using the trapezium rule, well, the height is going to be 1. 1 over 2. The first value is just here, and that's going to be 1. The last value is this one just here. This is the first value, this is the last value, and that is going to be this one just here. So first plus the last, plus 2 lots of what's left in the middle. Well, 4 is left in the middle and 9 is left in the middle. So 4 plus 9, and then we just calculate this. So it's going to be 1/2, what's that, 13, 26, 27, 43. So we can say that the area is approximately equal to 43 over 2, which is 21.5. The actual area using integration was 21. We were able to integrate that without any hassle at all because we could do it. It's a basic polynomial. Using the trapezium rule, we've ended up now with this particular estimate of 21.5. As we said, this was going to be an overestimate because of the nature of the curve. This is concave, so it's going like that. So if I put a trapezium there, when we drew the line, it would be slightly over the curve each time. Remember, these trapeziums have to be of equal width. So this would give us now an overestimate. So that is an over. If we have a curve that is convex or opens downwards, and I drew these up, let's put that there, that would be slightly below. and we would say that this is going to give us an underestimate. In later videos, again, we will look at examples of this. So, what happens if I increase this now from 3 strips to 6 strips? So we'll use a trapezium rule. So the trapezium rule will now do 6 strips. So 6 strips, so that gives rise to 7 ordinates. So 7 ordinates. So all I need to do now is my 4 minus 1 divided by 6. Now this is going to give me a half, and that's blindingly obvious anyway because we're going to split this up. So this time, and I'll draw this hopefully, in fact let's put the graph, let's see if I can draw it down here as well. Let's see if we got enough space. Let's go down here. Right, there we go, we got enough. So this time what I'm going to do is make the trapeziums now of a lower height. So this time what we're going to have is, let's put that on, let's choose red instead. I think that'll show better than white. So we're going to have one here, we're going to have, that is going to go just there. So that's my first one. So you can see now that straight away this is going to give me a better estimate as it's closer to the curvature of the curve. So that is going from there to there, and that is going up there. So straight away we can see now, compared to this one, where we've got this gap here, by increasing the number of strips, we're increasing the accuracy. So if we do that, we're going to go to that one, and we're going to keep going up, and let's just go there. So that's going to go there, that's going to go there. Not hugely accurate, again, my drawings, but hopefully it gives you some idea of what's going on. And then we just connect these up like so, and that's not a million miles off. So when I evaluate this, I'm expecting it to be closer to the actual value of 21. So let's set the table up, and again all we need to do is use the x and the y coordinates. So what we've got then is the following. So if we've got x, so x is going to be here. So what we've got is now 1, we've got 1.5, we've got 2, we've got 2.5, we've got 3, we've got 3.5, and then we've got 4. So again, this is going to give us 1. This is going to, 1.5 squared is 2.25. That's going to give us 4. That's going to give us 6.25. That's going to give us 9. That is going to give us, what's that going to give us? 12.25. 3.5 squared, 12.25, and that's going to give us now 16. Let's just check my 3.5 squared. I'm not going nuts. 3.5 squared should be 12.25. There we go. So all I've done now is simply put these in. So we can say that the area is approximately equal to. So this time we can see that h, remember it's h over 2, it's the first plus the last, plus 2 lots of everything added up, so the rest added. And of course you don't have to write this in the exam, hence why I'm using different things here. So the area is approximately equal to 1/2 divided by 2. So this time, instead of h being 1, h is going to be 1/2. The first, well that's going to again be 1, plus the last, which is 16, plus 2 lots of all of these added up. So we've got 2.25, plus the 4, plus the 6.25, plus now the 9, plus the 12.25, and then we will just work this out. So let's go ahead and do this in a calculator. I'm being a bit lazy. So 1/2 over 2 is a quarter. Then we've got now 1 plus 16, so that's 17, plus 2 lots now of 2.25, plus the 4, and I suppose you can do a lot of tidying up with this as well, plus the 6.25, plus the 9, plus the 12.25, and we'll just close that off. And that gives me now 21.125. So the area is approximately equal to 21.125. So let's just check I've got that in there right. So we can see that that is getting closer and closer to this 21 because I'm increasing the number of strips. We went from 21.5, which was pretty, well, it's okay. It's not outstanding, but that's what we end up getting. Should we do it with one more? This time what we're going to do, we'll do 1 to 4, and we'll do this now. So what we'll have then, let's do the integral. We'll go from 1 to 4 using the trapezium rule. So we'll do the trapezium rule, and we'll do now, we've just done 6 strips, so what we'll do is we'll do 5 strips. So they're not always going to give integer values, so let's do the 5 strips. So what we've got then is the following. We've got b minus a, so it's 4 minus 1 over now 5. So if we consider this, what we've got is each strip is going to be equal to, that's going to give me 3 divided by 5, which is going to be what, 0.6. So 3/5, 3 divided by 5 is 0.6. So all we're going to do is set this up with 5 strips. So let's put this in. So we'll have our x coordinates. Again, it's the same function. So x, and we'll have y. We've got 1, so we're going to have 1.6. We're going to have 2.2. We're going to have 2.8. We're going to have 3.4. And we're going to have 4. So 5 strips gives rise to 6 ordinates. So let's put this in. So 5 strips, 6 ordinates. All we would simply do is put these in and go ahead and work it out. So that's, you can put the values in. Now 5 strips is quite clearly going to give us a value somewhere in between the 21.5 that we found and the 21.25 that we found with 6 strips. 5 strips is quite clearly not going to be as good as 6 strips. So there we go, that's an introduction to the trapezium rule. Right, what I want to do is just, I'm just going to move on. If you want to stop the video now and go on to the questions, you can do. But what I'm going to do is just look at why this works and why it's first plus the last plus 2 lots of everything left in the middle. So let's go back to the, well, I wouldn't say it's a clumsy approximation, but the approximation using 3 strips. So what we've got then is something like this. So let's put this on. So let's just do that. So this is how it really works. What we've got down here, and I'll just put these on. Let's choose that. This one is going to be x0. This is going to be y0. This is going to be x1. This is going to be y1. This is going to be x2. This is going to be y2. This is going to be x3, and this is going to be y3. So, if we think about this now, what we've got is 3 different trapeziums. So I'll quickly sketch these, they're not going to be massively accurate. Then we've got the next one, which is going to be like so. Remember, all of these have the same height just here. They've all got a height of 1. So this is just h, and then we'll draw the last one. Then that one's going to be slightly higher, and it'll look like this. If we look at these now, so let's put these on. What we've got here, this is h, okay? This is h, and this is h, and that is the right angle just here. This length here is y0. Now, when we talk about y0 is simply, I've just substituted an x is 0. If x is 0, 1, and that's going to be 1. Now this length is going to be y1. It's going to be the y coordinate when we evaluate x1. If we look just here, this one, of course, is going to be y1. That height just there is y1. This one just here, this height, is going to be y2. So y2. Clearly the next trapezium is going to be y2, and then this one is going to be y3. If we just think of a general formula for the area of a trapezium, what we've got, if this side was A and this side was B, what we'd have is A plus B divided by 2 multiplied by the perpendicular height. So if we look, what we've got on this trapezium is y0 plus y1 over 2 multiplied by h. If we then add to that, we've got y1 plus y2 divided by 2 multiplied by h. Plus y2 plus y3 divided by 2 multiplied by h. You can see what's happening here. We've got this y0 and y3, but everything else appears twice. So y1 appears to be the height of the longer side of this trapezium and also the height of the shorter side of this trapezium. y2 is the longer side of this one and the shorter side of this one. So if we look at what we could do here, we could take this out. So the area is approximately equal to, it's just the sum of these. So taking out h over 2, that's a common factor here. What we're going to have here is y0 plus y1 plus y1 plus y2 plus y3 on here, plus y2 plus y3. So if we look at this, and if I just highlight them, what we've got here now is, so let's get the highlighter, that looks like highlighter. We've got y0 and y3. This is the first plus the last value of the y coordinates, but everything else in the middle, we've got y1 here, and we've got y1 just here. We've got y2 here, and we've got y2 here. So hopefully you can see now why this gives us here the area is approximately equal to h over 2, where h is just the height of the strip. Then we've got the first plus the last plus 2 lots of all of the others added, because they appear twice. This side becomes this side, so all other values, so all values are added. And again, you can word that how you want. And this takes us back to the crazy old formula that we're given in the formula book here. So in our particular case, n was 3. So we had now 1/2 h, where h is b minus a over n. That was a strip width. The first plus the last plus 2 lots of all of the others added up. But of course, we only had y1 and y2, because here what we had, of course, was n is 3, and that would give us y2, which would be this one just here. So there we go. I suppose I need to do that to keep the rigour of what we're doing. But essentially, the trapezium rule is this. Area is approximately equal to, it's not equal to, first plus last plus 2 lots of all of the other values added. Now that is the y coordinate, it's not the x coordinate. If we have n strips, we have n plus 1 ordinates. To find the height of a strip, you simply divide, you do b minus a divided by n, and that will tell you the interval that we're increasing by. We've got overestimates and underestimates, as we've seen. It's going to be an overestimate if our curve is concave, so we're curving upwards, and an underestimate if it's curving downwards. The more trapeziums, the more accurate our estimate is. So there we go, basic introduction, and then in a later video, next video, we're going to work through a range of different questions using functions that we can't integrate. I've used one that we can, just to give you the confidence and show you how it's done.